This video is going to look at the properties of the graphs of trigonometric functions. So before we begin, you should know a couple of vocabulary words. We're going to be looking at graphs that repeat themselves over and over and over again, and the period is how long it takes to go through a full cycle before we start repeating. Wave functions, which are what the sine and cosine functions are, they have amplitudes, and that tells you the height from the center of the graph to the highest or lowest point. And then last, we can talk about symmetry in graphs. Even graphs, if you fold them in half over the y-axis, they look exactly alike. So if I fold over the y-axis here, the left side matches the right side. Their line of symmetry is right down the center on the y-axis. And odd graphs, instead of folding in half over the y-axis or the x-axis, you kind of do this weird double fold, or you rotate your graph. Ooh, looks a little funky. But if I put my pencil, pretend that goes right through the origin. If I put my pencil right here and spin my paper upside down 180, the graph looks the exact same with respect to the axes. So when I rotate it upside down, it's still the same exact shape. For both of these, if you put your finger right in the center and rotate your graph, it looks the exact same with respect to the axes. And for here, if I put my finger right at the origin in the center and rotate my paper upside down, it looks the exact same with respect to the axes. Okay, why do we care about even and odd symmetry, and why do we care about periods and amplitudes and all that stuff? Let's do the symmetry first. Later on, we're going to do something called proofs, and when you do proofs, you're going to do a lot of manipulations with algebra. So even and odd is a lot easier to see when you're looking at graphs. So let's go on and figure out which functions are even and which ones are odd when we're looking at their graphs. Algebraically, an even function is a function that if you go in the negative direction or if you go in the positive direction, they will be the exact same y value. So no matter how far away I go backwards, if I go that same distance forwards on the graph, notice my y value is the same. Or here, if I go forwards and backwards that same exact amount, again, my y value is the same. So this is the algebraic way to describe even symmetry. There we go. All right, what about odd functions? All right, for odd functions, if I go backwards and if I go forwards, they're not going to be the same exact thing. They're going to be opposites. So you can write that either way. It just means that if I go backwards this amount on my graph, so I'm down here, and if I go forwards that same exact amount, my heights are still the same, but one's a positive value and one's a negative value. Okay, so what are these graphs that we're even applying all these properties to? What are we doing? We're going to look at graphs of sine and cosine, and tangent, and all 6 functions. But sine and cosine are the main ones we care about. But what does that really mean? It means we're going to take the sine function, and the y values here are going to tell us what is my sine fraction, and the x values here is what is my angle. Okay, so if I go around the unit circle and look at all of my sine values, all right, so at 0, my sine value here is 0. At pi over 6, my sine value, I guess I should label my y-axis. At pi over 6, my sine value is 1/2. At pi over 4, my sine value is square root 2 over 2, which is 0.7. At pi over 3, my sine value is square root 3 over 2, which is 0.8. And at 1/2 pi over 2, my sine value is 1. All right, if I filled in the blank for all these little angles between here, it would just connect the curve into a smooth curve. All right, let's keep going. We're at 2 pi over 3. This is my sine value, that's 0.8. At 3 pi over 4, my sine value is 0.7. At 5 pi over 6, my sine value is 1/2. At pi, my sine value is 0. If I kept doing this going all the way around my unit circle, it's really messy. So that's why I have a nice pretty graph. It would look like this. So my y value, my height of this little wave function here is telling you what is the sign fraction at my x value tells me the angles. And we just kept going around and around and around the unit circle. Same thing here. This is my cosine fraction at each angle on the unit circle, or it doesn't even need to be an angle on the unit circle. Just at any angle that I come up with, I can come up with my cosine fraction. Same thing. These are my tangent, my cosecant, my secant, and then my cotangent. These are all of these graphs. If I plot the different fractions at each angle, that's what I would come up with. So what do you need to know out of all this? The main important thing for you to know here is to be able to match each picture with the function. So you need to know that sine and cosine are both wave functions. They go up and down, up and down. Sine specifically crosses at 0. Cosine crosses the y-axis at 1. You need to know the specifics, not just the general shape, but specifically where do they cross the y-axis. You need to know that tangent and cotangent look a lot alike. They're this little spaghetti noodle shape here. But tangent, as you read from left to right, goes up and goes through 0. And cotangent, as you read from left to right, goes down and it doesn't touch the y-axis. And same thing for cosecant and secant. You need to know which one goes with which. If you know these 6 graphs, then you should be able to come up with all of these other properties here just based on pictures, because we've practiced this. We've practiced finding all of the properties of just random graphs that I've given you. Now I'm giving you specific graphs, but you know how to find the domain of a graph. You know how to find the range of a graph. So you can do that with these graphs once you know which picture goes with which function. But I'm going to do this one with you just because I think it is helpful to have a refresher and have someone help you a little bit through it. Okay, so let's talk about the domain and range and all this stuff for all these functions. Okay, for sine, remember, domain tells you what are my x values here. Well, my x values are angles. I can plug in whatever angle I want to, and I'm going to always be able to find a sine fraction. I don't have any undefined sine values. You use your calculator, type in 1 million, sine of 1 million. It's going to give you an angle. So my domain is negative infinity to infinity. There are not arrows drawn on the end of these graphs, but there should be. They're implied to be there. So my domain, it keeps going from left to right. There are no holes. There are no asymptotes. My domain is negative infinity to positive infinity. Range is your height from bottom to top. So the lowest that my graph ever gets to is right here at -1, and it actually hits -1. -1 is a sine fraction value at 3 pi over 2. And the highest that it gets on my graph is up here at 1. So at pi over 2, sine equals 1. So we use brackets because sine actually can be 1, and the sine fraction can also be -1. I don't care about relative max and min, so we can skip that, but your relative maxima is always going to be 1. I mean, notice it hits it in multiple times, but it's 1, and your relative minima is -1. Amplitude, that's the word that I just talked to you about. Amplitude is only something you use when you talk about wave functions. These two are wave functions because they look like waves, ocean waves. So from the middle line here, the center line here, to go to the highest point or to the lowest point, it should be the same. They should be somewhat symmetric. So to go from the center to the highest point or the center to the lowest point is your amplitude. And so my amplitude is 1. I go up 1, come back to center, down 1, back to center. Period. Notice that this graph just keeps repeating the same shape over and over and over again. Notice we go 0, up 1, back to center, down 1, back to center. Ooh, that's kind of hard to see. But if you'll notice, that's the shape that I just keep repeating over and over and over again. It's this little S curve that gets repeated over and over and over again. That shape, that green shape that's kind of hard to see, to go from here all the way to the end, oh, much better. The length there, the distance, the x value from 0 to 2 pi. So my period is 2 pi. It's just the same little S shape that I keep repeating over and over and over again. That tells you my period, and it is 2 pi. And finally, based on your graph, let's talk about even versus odd. Later on, we'll use the algebraic rules, but for now, Remember, even graphs, if you fold it in half over the y-axis, the left and right match. Odd graphs, if you turn it upside down from the center, from the origin, it's the exact same shape. And notice when I turn this one upside down, from the origin we go up one, back to center, down one, back to center, which is exactly what we did when it was right side up. Up one, back to center, down one, back to center. So this is an odd function. Every one of these functions will be even or odd. Okay, now that we've gone through that for sine, cosine is pretty much the exact same thing. My domain is negative infinity to positive infinity. When you look at your graph, there are no holes or asymptotes. My range, the lowest to highest, my range is from -1 to 1. I'm not going to worry about those. My amplitude from the center of my wave to the highest point, or the center to the lowest point, is 1. My period, this time I am repeating a slightly different shape, although I guess I could use that same S shape. But for cosine, it's easier for me to just start at the y-axis and think, okay, I'm going to center, down, center, peak. And just think of it, I'm using that kind of a curly V shape that I'm just going to repeat over and over and over. And just like with sine, that length there is from 0 to 2 pi. The only difference between cosine and sine is where they match up on the y-axis. Sine starts at 0 and goes up, down, up, down. Cosine starts at 1 and goes down, up. If I fold my graph in half over this y-axis, the left side will match the left side will match the right side, so that means this is an even function. All right, let's talk about the properties of these other 4 graphs because they look very different from sine and cosine. And they look very different from each other. But even though they're very different from each other, they have a lot of the same type of properties. And so we're going to repeat what we learned when we talk through tangent. All right, so tangent. Remember, when we find the domain of a graph, we're looking for anywhere we see holes or asymptotes. Okay, I don't have the asymptotes drawn in here specifically, but this graph goes all the way almost straight up here and almost straight down here. There are actually a million different asymptotes on this graph, and they all occur right here. So it makes things a little tricky. My domain is everything except the asymptotes, but I have to write out every single one of those asymptotes? That sounds like a nightmare. So let's jump down here and first talk about what our asymptotes are, or the equations of the asymptotes. Because we can come up with an equation. There's a pattern here, even though you may not believe me. Notice they're happening at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Have you noticed the pattern yet? Notice it's always over 2, and it's just we add a whole entire pi. 1/2 plus pi is 1.5 or 3/2. Plus pi is 2.5 or 5/2. Plus pi is 3.5 or 7/2. So notice they're always on the and a half. How do I write that? Because that's going to be, I don't know, I just have to explain that. You write that as it happened at pi over 2, and then we added k pi, or pi k. I don't know that it really matters the order here. We just kept adding 1 to our half every single time to get to the next asymptote. And you say where k is an integer, which just means a whole number, I can't spell, or you can use this notation here. And that just means k is a whole number. So if I start at a half, if I add any whole number, 1 billion, add 3, add -6, no matter how many whole numbers I get, as long as I'm adding a whole number to 1/2, I'm going to hit another asymptote. That's just how it works, which is lucky for us. Okay, so my vertical asymptote here is at pi over 2 plus k pi, where k is an integer or whole number. So for my domain, I can say all real numbers are negative infinity to positive infinity, except at the asymptotes. And the asymptote equation is pi over 2 plus k pi, where I'm going to use this weird math notation because it's less writing. Let's talk about the vertical asymptotes and the domain for the other three functions, because it seems really intense, but I don't think it's that bad. You know, I'm a math teacher, so I don't think any of this is that bad, but I don't think you'll think it's that bad either when we practice it. Okay, so let's talk about cosecant. It doesn't have the asymptotes drawn in for you, but I can draw them in right now. Okay, so notice I could use the same picture that I did before, where I drew in my asymptotes for tangent, as these. They're the same distance apart, so that's nice. I'm going from 0 to pi to 2 pi to 3 pi to 4 pi. That's really nice. I'm only on the whole number pi's. So how do I write that? You can either write, I usually pick pi because I like to have an actual number here. You can either write pi plus k pi, or you can just put k pi. Of course, we have to use the same notation we did before, where k is an integer. So as long as I'm any whole number pi value, I'm going to hit an asymptote. And just like before, my domain, remember we look for wholes or asymptotes, so my domain is all real numbers except where we have asymptotes, and we have asymptotes at k pi, where k is an integer. So really, it's not that bad. Notice our domain is the exact same thing, except I used a different equation because I used the vertical asymptote equation, which changed. We could do the same exact thing for secant and cosecant. Notice for secant, I'm going to actually use the same asymptotes that I drew in for whichever one I did earlier, because they're always pi apart. This one's pi halves, 3 pi halves, 5 pi halves. So instead of me starting at whole numbers, I'm at the half numbers again, just like we were with tangent. And just like before, my domain is all real numbers, negative infinity to positive infinity, except my asymptotes. And my asymptote equation is pi halves plus k pi, where k is an integer. I know this is a mouthful for you to write, but I'm trying to be specific with our notation, so for those of you who plan to go to calculus, you are on point and ready to go. All right, last one, cotangent. I'm not even going to redraw the asymptotes because, haha, they're the exact same distance apart like before, except now I'm on 0, pi, 2 pi, 3 pi, so now I'm on whole numbers again. Okay, so it looks really intense, but it's not too bad. You can either memorize the different properties, or once you know the shapes of the graph, I don't have any of this memorized. I have to think through what the graphs look like every single time before I can figure out where the asymptotes are and how to write my domain equation. So when you write these vertical asymptotes equations, I tend to follow the rule: the first positive asymptote plus k times your period, if you're tan or cotan, or first positive asymptote plus k times your period over 2, if you're secant or cosecant. Okay, so that leads us to talk about the periods of those two functions, but I just wanted to write this out for you because when we start doing transformations of these functions, you may want to come back to this video and just re-look at this right here, right there. Okay, let's talk about the periods real quick. Period is, remember, these shapes are all periodic. They just keep repeating over and over and over again. So when we talk about period, we're talking about if we just wanted to take a stamp here and just keep stamping over and over and over again, how wide would our stamp have to be? Well, for tangent, we're just taking this one little spaghetti noodle and repeating it over and over and over. Well, how wide is this spaghetti noodle here, or this shape here? It goes from negative pi halves to positive pi halves. So it's negative a half and positive a half. So think in terms of absolute value because we're just caring about distance here. That is negative a half and positive a half. If you add that whole distance together in absolute values, that is one entire whole pi. So from this half to this half our period here is pi. The same thing will happen down here when we talk about cotangent. It's a little clearer to see because our little spaghetti noodle, I don't know why I keep thinking of these as spaghetti noodles, but I do. It starts at 0 and goes to pi, and then we just keep repeating it. So from 0 to pi is pi. All right, well, what about cosecant and secant, these little u's? I can't just say pi, because if I just said pi, that would imply that I'm repeating just this u, this upper u, over and over and over again. And I didn't. I have an upper u and a lower u. This is the stamp that I'm going to repeat over and over and over again. If I wanted to continue on this graph, I need the upper and the lower. How wide is that? Well, that is from 0 to 2 pi. So my period here is 2 pi. I don't know if this makes it easier or harder that a lot of these periods and numbers repeat, but it's 2 pi just like sine and cosine. And secant will be the exact same way. I'm going to have an upper u and a lower u, so from -1/2 to +3/2, absolute value that to think about the distance from here to here. That is 2 whole pi's. I don't really care about range that much, but I know that it does get brought up and it's important. So the range for tangent and cotangent is all real numbers or -infinity to +infinity. Your tangent fraction can be anything that you want it to be, which is weird because, you know, sine and cosine fractions have to be between 0 and 1. Tangent and cotangent can be any number ever. And look at your range. It doesn't bottom out. It keeps going down and down and down forever, and it keeps going up and up and up forever. On the other hand, secant and cosecant, because they are reciprocals of sine and cosine, the range for sine and cosine was -1 to 1. Well, secant and cosecant, your range is everything but -1 to 1, kind of. -infinity all the way to -1, include -1, and then 1 to infinity, include +1. I'm glossing over that because I don't really care about range that much. And finally, let's talk about even and odd. I know I threw a lot at you in this video. I'm hoping that you can see where all the connections are and draw from previous classes. But let's do our last even and odd. So even and odd symmetry of graphs, remember, if I put my finger down in the center, or if I fold it over the y-axis, does the left and right meet? No, that means it's got to be odd. Or when I put my finger here at the origin and turn my graph upside down, that is the exact same picture as this graph with respect to the origin and everything. Everything's perfect. Okay, so this one has odd symmetry. This one has odd symmetry as well because when you flip it over the y-axis, the left and right don't match up because I would need to have a u up here too. Secant has even and cotangent has odd. Okay, there's your whole paper. Well, not quite because I can't zoom out. But I just have the graphs memorized and then go from there. You do whatever you need to.